Hi, welcome to my channel, JaberTime. Today I'm going to go over quick questions, 25 questions about properties of logarithms and some other formulas like change of base formula and how to solve natural log equations. Let's get started. Write log 225 base 15 equals 2 in exponential form. The way to do it, as you can see right here, log x base b equals y could be written as b to the y equals x in exponential form. And this is how we look at it. We read it as b to the power y. We go back this way in and we say equals x, provided that b cannot be negative and cannot be equal 1. So b has to be greater than 0 and it has to be positive, cannot equal 0, cannot be negative, and cannot equal 1. So here we go. This is our problem. It's quick questions. 15 to the power 2 equals 225. And that's how we look at it and read it in exponential form. 15 to the power 2 equals 225. Next one. Same concept. I have 4 questions just to practice. So this one right here will be 4 to the power 3 equals 64. Next one. To read this in exponential form, we say 3 to the power negative 5 equals 1 over 243. Next one. 9 to the power half, or square root of 9, equals 3. 9 to the power half, that means the square root of 9 equals 3. Okay, this is the other way around. We do have an exponential form. We need to write it in logarithmic form. Same concept, same formula. So we have this right here, as you could see, and we have the right hand side. We need to write it in log. So first we start with log base 7. 7 is our base. And if you look at it this way, 7 to the power what? 7 to the power 6. 7 to the power 6 equals 117,649. And that's the answer. One more. To write this in logarithmic form, we write log base 8, and after the equal sign it should be negative 3. This right here, 8 to the power negative 3 equals, we write inside 1 over 512. We call the inside part the argument. And that should do it. Another example. To write it in logarithmic form, we start with log base 8. And after the equal sign, we write the 2/3. Inside, we write 4. Okay, one more example. To write this in logarithmic form, we start with log base 3. Outside we have the 4, 3 to the power 4. Inside we have 81. Okay, that should do it for converting between logarithmic form and exponential form. Let's try something else. Evaluate the following. We still have the same formula right here. Well, to find this, let's call it y, and let's solve for y. Let's rewrite this in exponential form. 216 to the power y equals 6. So I'm assuming that 216 has a base 2. So it's a multiples of 6. Let's try on the side. 6 times 6 times 6 is actually 216. So 6 to the third is 216. So we could write 6 by itself. That's one option. To get rid of this 3, we raise both sides to the cubic root of 3, or raise both sides to the 1/3 to simplify this and make it 1. So 6 to the power 1 equals the cubic root or of 216, or 216 to the power 1/3. So that's one way to say it. 6 is actually 216 to the power 1/3. That shows that we are looking at the same color right here, the light blue, that y equals 1/3. And that should do it. So the key to start is we need to refer to this right here, call it y, and somehow manage these two to have the same exponent, or solve for y. Another example. To solve the following, we need to rewrite it or think exponential. Same formula. We have log. We need to see it in this format. So what we have, 4 to the power 5 over 2 should equal x. 4 to the power 5 over 2 equals x. To simplify this, we need to break down the 5 over 2 to two numbers, which is going to be half times 5. But half as an exponent means square root. Square root of 4 is 2. That's the square root of 4. We leave the 5 outside. So that says 2 to the power 5 and x equals 32. Let's try a different example. That's a different formula now. To solve the following, we need sometimes to check for extraneous solutions. The reason why, because sometimes when you solve these type of equations, you end up with answers that doesn't belong. You cannot have something, a number that when you plug it right here, gives you a negative argument. Log cannot be applied to negative numbers because log domain is usually to the positive side or the right side of the y-axis. Cannot equal to 0, cannot equal to 1, or sorry, cannot equal to negatives or 0. So notice that right here I wrote them with the same base 5 in a different color, because that's a formula. Log x equals log y, both with the same base b, if and only if x equals y. So we could jump from here to this statement straightforward. I do have this on the left side, similar to mine. So we're gonna say that the inside parts, which is called the arguments, they're gonna be equal. This becomes a quadratic equation that you could solve by factoring and move on. So, moving the 4x to the left, factoring the following, I see 2, -4, and -6. They all divide by 2, so let's take 2 out as a common factor first. Easier to factor. That's what I have. Okay? This part right here is factorable. It's going to be x minus 3 times x plus 1. Setting this equal to 0, we'll end up with two answers, 3 from this side, or this factor, and -1 from this factor. We have two answers, we need to double check. Let's try 3 first. See if 3 works. Plug it in both sides, right here in the first or the original equation. And after simplifying, you get log 12 base 5 equals log 12 base 5, which is fine. So 3 is a valid solution. If you try -1 for x, and plug it in the left hand side and the right hand side, or this right here, you end up with log -4. But log -4 is undefined. The domain for log is non-negatives and not 0, so only positive numbers. You could try it on the calculator. It's going to give you an error because it's out of the domain. Okay, so the only answer is x equals 3, -1 should be out, and that should do it. Let's try a different type of question. Use log 5 base 3 given to you as approximate to 1.465 to approximate the value of log 405 base 3. Well, that says that they are related somehow. We need to see log 405 somehow in terms of log 5. So they should be related. That's why in the same problem. Now 405, how many 5s in it? 81. If you divide by 5, you get 81. So I could rewrite 405 as 81 times 5. Here we go. Log 405 base 3 equals log 81 times 5 base 3. To break this down, a multiplication property will make it 2 logs with the same base 3. This is what we have. This is given to me to use up here, and this one we don't need a calculator to do it. It's designed or planned to be done without calculator. Let me show you how. 81 is multiples of 3. Let's go back right here. 81 is multiples of 3. It's 3 to the power 4. This 4, we could pull it all the way outside, and log 3 base 3 is 1. So that's going to end up just 4. 4 plus this number that was given to me up here. Add them up. So it's 5.465. And that should do it. One more. Log 1/6 ln, solve 1/6 ln 5x equals 2 and round to the nearest 10,000ths. So we need to round it to 4 digits. There's different ways of doing it. So the basic rule that we could apply is log m to the power n equals n log m. Of course, base b, base b. It's kind of like we pull the n all the way up front. And we have another rule that says log x equals y. We could rewrite it back in exponential form as b to the power y equals x. Going back to the problem. So we have the problem right here. I could take the 1/6 up here. That's an option. But then we're going to write e to the power 2 equals and so on. Here's another way. Multiplying both sides by 6 to leave ln alone by itself will force the 2 to be 12. As you could see, times 6 times 6. This will cancel. 6 times 2 is 12. Think about ln. Natural log is a log with base e. That's why we call it natural log, to distinguish between natural log and the common log. The common log is base 10. So this is base e. So here's e, and let's use this idea. We need to rewrite this in exponential form. B to the power y equals x. E to the power 12 equals 5x. We need to solve for x. So we divide both sides by 5. That becomes x equals 1/5 e to the power 12. Of course, this is with a calculator because we need to round to the nearest 10,000ths. Just plug it in the calculator and you get the following number. For 10,000ths, we need 4 digits. 8 is too high to ignore. So the 2 becomes 3. And that should do it for number 13. Let's try another example. Solve the following. Well, the left side is a sum of 2 logs or 2 lns. We need to put it back in 1 log using the product. So log m plus log n base b equals log m times n. Of course, the same base b. So on the left, it's base e. So this rule applies also to what we have. The left side is a sum of two lengths or two logs. That's what we have. We need to put it as one log. So that becomes len 3x multiplied by 2x. That is 6x to the second. Then we could use the exponential form from log e to the power 9 equals what's inside, which is 6x to the second. We need to solve for x, so let's clean it up. Divide both sides by 6, or multiply both sides by 1 over 6. So x to the second equals e to the 9 over 6. Take the square root of both sides to leave x alone. Use the calculator and round to 4 digits. And that's the answer. Next, solve the following. This is a difference. The difference becomes a quotient. This is the formula. A difference of two logs becomes one log with m over n. So that's what's going to be applied to the left-hand side. And later on, we're going to use the log to exponential. So I have this 56 divided by x. Same base, as you could see. If they are the same base, we could conclude that the arguments are the same. So we drop the logs and we write x equals y. So 56 over x should equal to 7. No more logs. Cross multiply, solve for x. So 7x on one side equals 56 times 1. Divide both sides by 7. And simplify this. This one is not rounded to decimal part because it's evenly divided, or divides evenly. 56 divided by 7 is 8, and that should do it. Number 16. Write the following expression as a single logarithm. One way to do it, since I see 3's here and 9 is actually 3 times 3, I could think about the 9 as 3 to the second. Here we go. Then applying this rule, going from left to right, I could take the n all the way up front, as you could see right here. So this 2 act like my n, so I'm going to take it to the front. Just like this. So this becomes 3 len 3 minus 2 len 3, which is just 1 len 3. In short, it's just len 3. And that should do it. Number 17. Write the following as a single logarithms. Here's some rules to keep in mind. We'll use them as we go. We need to simplify the following. So I could take the 1/3 back in, because the 1/3, sorry, one more time. I could take the 1/3 back in. It's going to look like 8 to the power 1/3, which is cubic root of 8. And we could write the 9 as 3 to the second. So here we go. That's what we have. Next, with this rule, we could take the 2 up front, just like the previous example. And this right here is a cubic root of 8. Cubic root of 8 is 2. And this becomes 2 len 3. Next, I have 2 len 3, take away 1 len 3. If you read it this way, it's much better than saying minus len 3 plus 2 len 3. So 2 len 3 minus 1 len 3 will be 1 len 3. This is a sum. I have a sum with the same base. I could combine them to one log because they want me to write it as a single logarithm. So you write this from a sum of two logs to a product of the arguments with one log. That's going to be len 2 multiplied by 3, which is in short len 6, and that should do it. One more practice. Write 2 ln x plus ln 3 minus ln y as a single logarithms. Let's write the formulas. Let's take the 2 back in, just like that. Take the 2 back in, like the first formula. So it's ln x to the second plus ln 3 minus ln y. These two are 2 lns with the same base e, with a sum in between them. We could write this as 1 log or 1 ln with a product of the 2 arguments. So this part right here becomes ln x to the second multiplied by 3. Or we could simplify this and write the 3 up front. Much better to look at than x to the second times 3. We say 3x to the second. Now let's look at the subtraction. I have subtraction between 2 logs with the same base. So we rewrite it as 1 log with the quotient of the arguments. And that's what I'm looking at. I have a subtraction. I have a subtraction between 2 logs. Those are logs but base e. Make it 1 log, and that should do it. So it's going to be ln, 1 ln, or 1 log with base e of 3x to the second divided by y. One more. Use the change of base formula to approximate the value of the given logarithm to the nearest 10 thousandths. Log 22 base 4. Here's the formula. You could use log n base 10 or any base, but we choose base 10 because calculators do have the common log and they do have the natural log. So this is the problem, log 22 base 4. Using this idea, usually we don't write it 10. If we just write log, it means base 10, the common log. That becomes log 22 base 10 over log 4 base 10, or in short we say log 22 divided by log 4. Just apply it to the calculator, divide, and you get this much. We need to round to 10 thousandths. That means 4 digits after the 0. Looking at the numbers right here, 1580. Looking at 1, that's too low. So 7 is my last number, and we just drop the 1 and after. Next, solve exponential equations with base e. This is a little bit different, and we're going to round also to the nearest 10 thousandths. Here's the formula that we're going to be applying. Whenever you have e to the x and you want to cancel e, ln is the inverse function of the exponential functions with base e, so they cancel each other. The input here is x. Applying ln after e takes you back to the same start, which is x. They cancel each other, kind of like you could slash them and bring the x down. We need to have this applied here, but first we need to clean everything and leave e alone without the minus 2, without the 8. Here we go. Let's subtract 8 from both sides. That gives me on the left negative 2 e to the power x plus 3. On the right side, after we cancel this, I have negative 14 minus 8, which is negative 22. This is still in my way. We have to clean it up before we apply this rule. So we're going to divide both sides by negative 2. This becomes e to the power x plus 3 equals positive 11. Now let's apply ln to both sides so you could see this on the left. Put ln on the left and put ln on the right side. That and that cancels and brings down the x plus 3. So we have x plus 3 equals ln 11. Subtract 3 from both sides. I have negative 3 plus ln 11 on the right side. Using the calculator, I get the approximate answer, negative 0.6021. Let's practice another example of the same concept. E to the power 3x equals 30. We need to apply this. To get x down, we apply ln to cancel the e. So here's the problem. Let's apply len to both sides. This len and e cancels. 3x stays by itself, equals len 30. We need x by itself, so I'm going to divide both sides by 3. And I get x equals len 30 all divided by 3. With the calculator, I see the following. 3 is lower than 5, so we just drop it. Here's the answer. Okay, now here's solve natural log logarithms, but we're not giving e, we're giving len. That's the coming example. Take a look. This time we have len, not e. We need to cancel len. To apply the inverse, that's e to the x. This is what we have. So if you have something like len x, but with base e, so it's e to the power len x. E and len are inverse functions. They are going to cancel. It's almost like you slash them right here, you cancel them, and you bring the x down. So x by itself. Here's the problem. What do I mean? To apply this right here, we need to have those as exponents with base e, just like this. Left hand side is just like this. Len and e will cancel each other, and x minus 6 drops down right here by itself. Just like this, x drops down by itself. So we have on the left x minus 6, on the right side e to the first, or just e. Add 6 to both sides to leave x alone. And I have x equals e plus 6. Since they want me to evaluate and round, we reach out to the calculator. E is about 2.718, and we add it to 6, and we end up with 8.718281828. Well, to round to the nearest 10,000s, we look at the first 4 digits, but 8 is too high, so we make the 2 3 and we drop what comes after that. Okay, another example of the same type. Len 3x equals 2. We're going to apply the same thing to cancel the len and reach out to the 3x. We raise both sides on top of the bases e. Here's what we have. Len 3x equals 2. This becomes e to the power len 3x equals e to the power 2. Of course, you could just rewrite this as e to the power 2 equals what's inside, which is the same concept. But let's just keep it consistent with this rule right here. So the left-hand side, these two cancels. We get the 3x by itself, e to the second. We need x by itself. We divide both sides by 3. So x equals e to the second, divide by 3. Calculator time. We get the following. 1 is too low, we just drop it. And the answer is 2.4630. We're almost there. Let's go to a different type of problems. Use the natural logarithm to solve the following. 3 to the power x equals 0.4. And we need also to round. In this case, we could rewrite this as len, or do the following. Len m to the power n equals n. Len m, it's like you bring the n down. But I have the problem this way, there's no len. So let's apply len to both sides. When you apply len to both sides, I could use this formula and bring the n up front, bring the 3 up front. So I have x len 3 equals len 0.4. Well, why apply len? Because I need to x to be up front. It's kind of hard to reach and look at it while it's an exponent. We're solving for x. So I need the x to be loose up front, not as an exponent. And that's one way to do it. Divide both sides by len 3 to leave x alone. This cancels, and we end up with x equal len 0.4 divided by len 3. Use the calculator to divide len 0.4 by len 3, and that's what I have. after 4 digits to refer to 10,000s, because that's ones, tens, hundreds, and tens, hundreds, thousands, 10,000s. We don't have ones on the right side, ones on the left side, or units. So tens, hundreds, thousands, 10,000s. 4 is too low, we drop it, and we just keep what we have right here. Last question. Use the natural logarithm to solve the following. We need to clean it up first. What do I mean? We need to add 1 to both sides. Becomes 2e to the x equals 12. Divide both sides by 2, because we need ex by itself. I get e to the x equals 6. Now we could apply this rule. Apply ln to both sides. Bring x down, ln e is 1. Or think about e and ln cancels, and x becomes by itself. X equals ln 6. Use the calculator because we need to round. I have the following. 5 is too high. 5 over up. We round the digit to the left up by 1 unit. So this becomes 1.7918. And that should do it. It's a quick 25 questions about logarithms and equations. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.